Okay, hello everyone. Let's go ahead and take a look at the Poisson distribution. And it is going to be a statistical distribution that we need to cover for the higher level content. Now, what is the Poisson distribution? And we have to go back to think about what we're dealing with. We had the normal distribution, we also had the binomial distribution, and those are the two that we really looked at in the standard level material. The Poisson distribution is going to be the last distribution that we're going to look at for the higher level core material. And it is used basically to determine the probability of obtaining a certain number of successes that can take place in a certain interval of time or space. So that's the key to distinguish between a normal distribution, a standard normal distribution, a binomial distribution, and a Poisson distribution. The Poisson distribution is based upon an interval of time or space. Okay, and when we go ahead and take a look at an example, you'll see exactly how that time or space comes into play. But let's just go ahead and take a look at a couple of things with regards to the Poisson distribution. And we can say that the mean, of course, which is the expectation, is going to be based upon frequency tables. And the reason for that, of course, is we're dealing with an interval of time or space. And within a particular amount of time, you're just looking for how often that particular event occurs. And so you're dealing with frequency tables. So this is nothing different from before in the sense that we just take a look at the frequency table, take a look at that particular value multiplied by its frequency, add all of those up and divide by the total number of frequencies, and you come up with the parameter m, or the mean. Now, if we wanted to go ahead and look at the Poisson distribution, the Poisson distribution is a fixed formula, and it's going to be m to the x times it by e to the negative m divided by x factorial. Now, the one thing that you should notice about this is that the only parameter that you have is m. Once you know what the mean is, you can go ahead and determine the probabilities that would be generated using the Poisson distribution formula. So another interesting fact that we'll take a look a little bit more in depth in class is that the variance of x, if the distribution is Poisson, is also going to be equal to m, which of course is going to be equal to the standard deviation squared. And the shorthand notation of that is going to be this here. Now, there's a couple of necessary conditions before we can actually go ahead and say that a particular frequency distribution is going to fit within the Poisson distribution, and therefore we can use the model to make generalizations. And here are the three necessary conditions. One, the average number of recurrences is constant for each interval. Okay, two, the probability of more than one occurrence in a given interval is very small, which is generally 10% or less. And the number of occurrences in disjoint intervals is independent of each other. Now, we'll go ahead and take a look at some of these conditions and how it applies to some of those Poisson distributions that we will see in these exercises. Okay? Okay, so let's go ahead and take a look at a particular example here. Let's say, for example, a shop receives X phone calls between 9 a.m. and 9:15 every Friday. Okay, now let's go ahead and describe what is actually happening here based upon this frequency table. Now, the first thing that we need to notice is that we're talking about the number of phone calls between 9 a.m. and 9:15 every Friday. So what that means then is we're talking about a particular interval of time or space. In this case, it's time. So between 9 a.m. and 9:15 on Fridays, how many phone calls does this particular shop receive? Now, how many Fridays are we talking about here? Well, in order to go ahead and determine that, we need to go ahead and determine the frequency. And if we go ahead and add up 12, 18, 12, 6, 3, 0, and 1, we come up with 52. So, generally speaking, this is like about a year's worth of record keeping between 9 a.m. and 9:15 every Friday. So let's say, for example, this is the first Friday, there are 3 calls, I put in 1 there. Next Friday, there were only 2 calls, I put in 1 there. So we're doing this every Friday from 9 a.m. to 9:15 for 1 year, and this is the information that we compile. So for between 9 a.m. and 9:15 on any particular Friday, you know, we had, for no phone calls, there were 12 Fridays where there were no phone calls. There are 18 Fridays where there was just 1 phone call between 9 a.m. and 9:15. etc., etc. So now, being that we're dealing with an interval of time or space, and we're looking at a frequency distribution chart based upon this information here, then we can go ahead and see whether or not this information actually suits the Poisson model. So what we'll go ahead and do is let's go ahead and figure out first of all what the mean is, or using the expectation. We can go ahead and calculate what that is by just saying 0 times by 12 plus 1 times by 18, etc., and divided by 52 because there's about 52 Fridays that we've accounted for here. So what we come out with is 1.5, and we come out with the mean being 1.5, and therefore for the Poisson distribution, the parameter m is going to be 1.5 as well. So I can say then that p, the probability of x being equal to x of I, is going to be exactly the same thing as 1.5 raised to the x power e to the negative 1.5 divided by x factorial. Now if we go ahead and put that into our calculator, we're going to come up with a whole bunch of probabilities. Now what we want to do though is we want to determine whether or not this model actually fits the data, and whether or not this model is an appropriate model to use for this data. Now if I go ahead and take a look at the probabilities for each one of these intervals here, for each one of these frequency columns, and if I go ahead and multiply it by 52, because that's the total number of frequencies that we have, then what you'll see is we come up with 11.6, etc., etc. Now, if we go ahead and take a look at this, if those values are very close to the actual frequencies that were generated by record keeping throughout the year in this particular case, then we can say then that the Poisson distribution is actually an appropriate model for this particular situation. So if we go ahead and just take a look at how close these values are, we can now go ahead and say that the Poisson distribution is an appropriate statistical model for this data, and we can use it to generalize into the future. So there's a very simple way that we can go ahead and analyze a particular distribution based upon an interval of time or space, and we can go ahead and use our frequency charts to go ahead and establish what the mean is, substitute that into the parameter m for our Poisson distribution, and then go ahead and determine whether or not the model fits the particular reality well or not. Okay? So we'll go ahead and take a look at doing more calculations and practicing this a bit more when we see each other in class. So we'll see you then. Bye-bye.